Hello friends, in this video I'd like to solve the following problem from the Romanian National Mathematical Olympiad for 7th graders 2007, problem number 4. Let m be greater than 1, m and n are integers, such that 2 to the power 2m plus 1 is greater than or equal n squared. Show that, in fact, stronger inequality is true. 2 to the power 2m plus 1 is greater than or equal n squared plus 7. So this problem is not terribly difficult, as it is given to 7th graders. Here are my hints. Go case by case, so write 2 to the power 2m plus 1 equals n squared plus r, and dismiss every case from r equals 0 to r equals 6 by various methods. And moreover, for cases where r is divisible either by 3 or 5, you may wish to find first all possible quadratic residues modulo 3 and 5. So give this problem a try and I will see you in just a minute. Okay, so here is my solution. So let's go case by case. So case number 1. Let's see, 2 to the power 2m plus 1 equals n squared. Is it possible? No, it isn't, because we can write it in the following way. 2 equals n over 2 to the power of m squared. And on the right hand side we have a square of a rational number and square root of 2 is irrational. So we have a contradiction. Impossible. Oh, alright, let's consider second case. 2 to the power 2m plus 1 equals n squared plus 1. What now? Well, in this case, notice that n must be odd. N must be odd, i.e. n can be written as 2k plus 1 for some integer k. Okay, let's plug it in. And we get the following. 2 to the power 2m plus 1 equals n squared. It's 4k squared plus 4k plus 1, so plus 2. And now we can divide by 2. We have 2 to the power 2m equals, and I can factor out number 2, or maybe not. Wait. And we have a problem, because remember that m is greater than 1, so this is even. This part is even as well, but this part is odd. Equality cannot happen. Contradiction. Impossible. Third case. 2 to the power 2m plus 1 equals n squared plus 3. And I will do at the same time case where it equals n squared plus 6. I will do them both. I will reduce reduction modulo 3. Let's take a look. If I reduce my equation modulo 3, on the left hand side, in either case, I have 2 is congruent to minus 1. So minus 1 to the power 2m plus 1 should be congruent to n squared modulo 3, because 3 and 6 are congruent to 0. And minus 1 to an odd power is minus 1. So it should be true that minus 1 is congruent to n squared modulo 3, but it is impossible. Why? Because what are the possible quadratic residues? Well, if I take 0 squared is congruent to 1. And plus or minus 1 are both congruent to 1 modulo 3. Minus 1 does not appear on this list. So we get yet another contradiction. We can say technically that our number is quadratic non-residue. -1 is quadratic non-residue modulo 3, so we don't get any result here. Okay, so it's done. Penultimate case, case number 4. 2 to the power 2m plus 1 equals n squared plus 4. And now notice that in this case, n must be even. N must be even. And we can divide by 4. So we have 2 to the power 2m minus 1, because we divide by 4, equals n over 2 squared plus 1. And if you look closely, it's very similar to case number 2. We get a very similar equation, so reasoning is also similar. So that means that n over 2 must be odd. I.e. n over 2 can be written as 2l plus 1 for some integer l, and we get the following: 2 to the power 2m minus 1 equals 4l squared plus 4l plus 2, and after division by 2, we get 2 to the power 2m minus 1 equals 2l squared plus 2l plus 1. And now it's the only place where we will use the assumption that m is strictly greater than 1. It's strictly greater than 1, so our exponent is strictly greater than 0 because of our assumption. So it's even. So here we have even number, here we have even number, and here we have odd number. So we get contradiction. And finally, last case, case number 5 and final, 2 to the power 2, maybe write it in speech color, 2 to the power 2m plus 1 equals n squared plus 5, and this time I will consider reduction modulo 5. Reduction modulo 5, and I will get the following. What exactly? Well, on the left hand side, we have 2 times 4 to the power of m is congruent to n squared. Modulo 5, of course. But what is 4? 4 is congruent to minus 1. So we have n squared is congruent to 2 times minus 1 to the power of m, modulo 5. Very well. And that means, in other words, n squared is congruent to either 2 or minus 2. And now I will just demonstrate that neither of these numbers is a quadratic residue. How can I do it? Well, by considering 0 squared. Well, 0 squared is congruent to 0. Plus minus 1 squared is congruent to 1. Plus minus 2 squared is congruent to 4, and 4 is congruent to minus 1. Neither 2 nor minus 2 appears on this list, so we get yet another contradiction. Plus minus 2 are quadratic non-residues, modulo 5. And case n squared plus 6 was already covered here. So these 5 cases are impossible. So it must be the case. It must be the case that 2 to the power 2m plus 1 is in fact greater than or equal n squared plus 7. And that closes our proof. It's exactly what we wanted. Thank you for watching, and I will see you next time. Goodbye.